Welcome everyone. We are continuing with the 2D point group. So, last class we saw that in 2 dimensions we can have the rotational point groups, and that is 1, 2, 3, 4 and 6, and then you can have also a mirror point group, that is you can have a single mirror M. And then we saw that M can be combined with two-fold to give you a point group 2 mm, and 2 mm turned out to be an interesting point group in the sense that if I draw the stereogram of that point group 2 mm, then you have a two-fold, and you have a mirror passing through the two-fold. But at the same time you generate another mirror which is at 90 degree to the two-fold. Now, two-fold does not rotate things by 90 degree, but it interacts with the two mirror operation to generate this two-fold which is at 90 degree. So, the rotation associated with the two-fold is 180 degree, but mirrors are separated by 90 degree. So, and we wrote you can write the group elements so that's identity. Identity, as you know, is a requirement for all group, so that will always be there. Then you have the two-fold operation, and then you have two mirrors which you can call M10 and M01. Similarly, you can work out what will happen if you add a mirror to a three-fold axis. So, let us try to do that. So, 3 plus a mirror which is passing through the three-fold. So, let us call that a parallel mirror, because any axis you can have a mirror passing through the axis or a mirror perpendicular to the axis. So, since it is a three-fold, so I need to rotate by 120 degree. So, I draw reference lines at 60 degrees to guide myself. So, I draw 3 lines. So, till now these are not symmetry operations, these are only the primitive circle of the stereographic projection, and I have 3 reference lines, or you are thinking in terms of 3D, then you can think of it as 3 vertical planes separated by 60 degrees to guide me through the three-fold rotation. So, I have the vertical three-fold, and I add just one mirror. So, I start with a motif, a right-handed motif, and first I do not worry about the mirror, I just look at the existence of the three-fold. So, I rotate this motif by 120 degree. So, I get another motif there and another 120 degree. So, I get another motif there, and rotation does not change handedness. So, they will all be of the same handedness. Rotation does not, a vertical rotation axis will not change the height also. So, all of them are at the same height, you can think. And then I note the existence of the mirror, and I start reflecting the objects into this mirror. So, I create another motif. Now, this time the handedness is changed, which is indicated by the comma inside. Height does not change. So, I get this. if I reflect the rightmost motif there, the second motif, then I generate another right handed motif there. And finally, if I rotate the third, sorry, reflect the third motif, I get its counterpart there. So, now I have 6 general positions or 6 motif generated by application of the threefold and a mirror. But then I notice, if you notice carefully, that these other 2 mirrors have automatically got generated, because you can see that these 2 motifs are related by mirror, these 2 motifs are also related by that mirror, and similarly these last 2, they are also reflected in this new mirror. And not only that, I also generate this third mirror. So, all my original reference lines actually got converted into mirrors. So, this point group again is named after the principal axis, that is 3, and then I added a parallel M. So, 3 M. I do not put another M here like I did in the 2 mm case. In the 2 mm case, I had put another mirror, because the second mirror was a surprise mirror. I did not expect a 90-degree rotation by a two-fold. Here the 3 mirrors which you are getting, although they are at 60-degree, but you can see that they are also at 120-degree, and 120-degree rotation I was expecting from threefold. So, all the mirrors are also equivalent by the threefold symmetry I can generate. So, if I call this mirror as my first mirror and I give it a 120-degree rotation, I get this as the second mirror. From here I go to 120-degree, I get that second mirror. Then if I give another 120-degree rotation, I get that third mirror. So, all the 3 mirrors are related to each other, all the 3 mirrors are related to each other by 120-degree rotation. So, there is only one set of symmetry equivalent mirrors. So, notation takes care of that and does not write 2 m's, but just 1 m in the case of 3. So, you have 3 m, you can write the operations. The number of symmetry operations in a group and the number of general positions in its stereogram are always the same. So, you can see that I have generated 6 general positions in the stereogram. So, I know that there will be 6 operations in the point group. So, if you start calling, let us say, let me call this the first identity will be the first operation, and each operation will correspond to a general position. So, whatever is your starting position is the identity, because you are not doing anything, you just put it there. So, this one, so that is an identity. Then you had an anti-clockwise rotation of 3, that is the 3 plus. So, you have 3 plus, and then further you have 2 times 3 plus, which is 3 square, which is this one, or 3 plus is square, but instead of writing square you feel more convenient if you take this up as a negative rotation. So, you write it as 3 minus, so 3 minus, and then you have 3 mirrors. So, you can write those mirrors as, now you should use some designation for writing these mirrors. So, if you take this as your x axis, so let us say 1 0, then this is your y axis, that is 0 1, then the middle one direction is 1 1, this is bar 1 0 in terms of direction I am writing, and this one is bar 1. Sorry, my diagram is getting cluttered, but I hope you are following it. And then I have this one which is 0 bar 1. These are the Miller indices of these directions in which mirrors are lying. So, the 1 0 mirror is perpendicular to this direction, and this direction will be sum of 1 1 and 0 1. So, this direction is actually 1 2. So, this first mirror, the vertical mirror, is the normal to that is 1 2. So, I will call that a 1 2 mirror. The second one, the second mirror labeled here, this one. So, this mirror, the normal direction is, you can see, a 0 1 bar direction. This direction is normal to the, no sorry, this direction will be normal. One has to be little careful, I am not being very careful. So, this direction is normal to this. So, you can see that this direction is sum of 1 0 and 0 bar 1. So, that will be 1 bar 1 direction. So, the second mirror is M 1 bar 1, and finally, the third mirror which is this one. So, the normal to that will be this direction, which is sum of 1 0 and 1 1. So, that will be 2 1. Essentially, you have 3 mirrors, and these are not so difficult to work out as we have done just now, but do not worry, you have 3 mirrors and you require 3 different labels to label those mirrors. And one standard practice of labeling mirrors is to label them by the direction which is normal to them, the plane normal. So, that way I have the 3 rotations and the 3 mirrors. So, the group is of order 6. Now, you have 4 plus a parallel mirror. Now, you can work that out easily. So, I start with again a primitive circle. It is a 4-fold. So, I take 2 reference lines at 90 degree, place my 4-fold in the center. I start with a general position and a general motif. So, a right handed motif, 90 degree rotation will generate 4 more motifs of the same handedness. So, that is all will be there if it was just the point group 4. Point group 4 is of order 4, 4 general positions, 4 operations, but I want to combine it with a mirror plane now. So, I again combine it with a mirror plane. So, I put one mirror plane and see what effect it has on the motifs. So, it will start generating new motifs, and since it is reflected, the handedness change. So, let me number, it was the first one, then second, third, fourth, and the first one reflects into fifth, second one in sixth, third one in 7th, and fourth one in 8th, all with changed handedness. Here I am showing them with changed color also. And now you have used to not being surprised by new symmetry elements getting generated. So, you can see that a mirror plane has got generated exactly at 90 degree, because that is what will relate 2 to 8, 4 to 6, 1 to 7 and 3 to 5. But that is not all. You have two mirrors at 45 degree also, just like it had happened in 2 that you had mid mirrors. Here also you created 2 more mid mirrors. So, you have generated a point group which is called 4 mm. Now, you can see that there are 8 general positions. So, the point group also has 8 operations: 1, 4 plus 90 degree rotation, 4 plus is square, that will be 180 degree rotation. So, instead of writing 4 plus is square, we write it as 2, which is 180 degree rotation. Then 4 plus cube, which is 270 degree rotation, which is equal to minus 90 degree rotation. So, we write it as 4 minus. And then there are mirrors. Here the mirror designations are easier. You just have mirror perpendicular to 1 0, mirror perpendicular to 0 1, because these will be the direction. This direction is 1 0, this direction is 0 1, this direction is 1 1, and this direction is 1 1 bar 1. And you have mirrors perpendicular to all these directions. So, 1 0, 0 1, 1 1, bar 1. We did the matrix method justification for 2 mm. We saw that how a 2 and M10 when combined through matrix gave you the matrix for M01. The same exercise can be extended to these. We are not doing it, but if you combine any of these, so for example 4 plus and M10, you should get some other mirror, because 4 plus is type 1, M10 is type 2. So, combination will automatically give you some other mirror from this set. It is a group, so it has to be closed, it cannot go out of the group operations. So, any combination will produce some other combination, and that can be easily checked by the matrix method. So, here again the angle between the nearest mirrors are 45 degree. So, which seems to be half of the 90 degree rotation associated with 4 fold. So, everywhere you are seeing that the mirrors are occurring at half the angle of the rotation axis, and the last one is no exception to this, that is 6 mm. So, I again need 3 lines at 60 degree to guide me through 60 degree rotations, and I start with a motif. I start with a 6 fold in the center, and I start with a general motif. So, that gives me 6 general position of same handedness through this 6 fold axis. Then I introduce the mirror. and as usual all I have to do is to introduce only one mirror, which will then generate all other mirrors automatically. So, mirror will start reflecting. So, 1 will be reflected into 7, 2 will be reflected into 8, 6 will be reflected into 9, sorry, let me go sequentially. So, 3 will be reflected into 3 will be reflected into 9, 4 will be reflected into 10, 5 will be reflected into 11, and 6 will be reflected into 12. So, that is just the action of one mirror on all the 6 general positions which has got generated by the 6th fold, but now these mirrors come on their own. So, geometrically we are saying that they come on their own. Algebraically or in terms of the group operation, they are coming by combination of the symmetry operations within the group. So, these are 3 mirrors, but there are mirrors in between also. So, 3 mirrors at 60 degree, but because of these 3 extra mirrors, now the mirror angles will reduce to 30 degree. So, again half of the rotation of the symmetry axis. So, this is the 6 mm point group. Which is 1, 6 plus, 6 plus square will become 3 plus because 120 degree rotation, 6 plus cube will be 180 degree rotation, that is 2. Then you have 3 minus, 6 minus, and you have 6 mirrors. You can again find their designations by normals. So, find their normals. So, you will have 6 mirrors. So, the order is 12 now. 12 operations are there. So, 6 rotation operations and 6 mirror operations in each of the 6 mirror planes.